Okay, hi guys. So in this lecture, we'll be starting off with comparison of rate of acid catalyzed dehydration in the following compounds. So you have to compare rate of acid catalyzed, or basically I'm trying to say even reaction, acid catalyzed dehydration in the following compounds. Okay, so we have something like this. The first example here is phenol, then this one, this is the A, B, C. C is nothing but this one, D is this one, and finally E is this one. Okay, so as you can see, the formation of highly unstable aryl carbocation can happen in this case, hence the A's rate would be the least. A is out of the picture, and when E on the carbocation is formed at this carbon position, hence resonating structures can be there, or the conjugation of double bond or pi electrons with carbocation is there in E compound, hence E's rate would be highest. Okay, now let us compare between B, C, and D. Obviously, if you look closely on them, you can see that if we have B, then the number of alpha hydrogen at this carbon is obviously 1 2 3 4 5 6 7, and at this we have number of alpha hydrogen as 1 2 3, and at this we have number of alpha hydrogen as only 1. So what would be the order BCD? Okay, and we are not talking about rearrangement case over here, because this is the first, or in the RDS step, at this carbon, and at this carbon only the first positive charge would be there. Obviously after rearrangement, you can say that the major product in all those BCD cases would be the same, but still we are comparing, and for the comparison sake we need to compare the first intermediate which is formed in RDS. Okay, let's look at the second example. We have something like this. And this. Okay, so just compare the intermediate when this carbon gets a positive charge, when this carbon gets a positive charge, and when this carbon gets a positive charge. This is a 3 degree, this is a 2 degree, and this is a 1 degree. I need not explain much, but this would be the order. Okay, so just a thing here, that just a note here, that actually what happens in SN1 and SN2, those are irreversible reactions. Okay, but in even reaction, that is a reversible reaction. Okay, so if the stability of carbocation is not much, and also the rate of the RDS is the activation energy for RDS is too higher, then actually this is a reversible reaction, and in these cases no reaction can also take place. Okay, so yeah, and now let me take a random topic here. A small note is, what about ambient? I'll just introduce a concept to you which is called ambient nucleophile. Which is nothing but, if you look at the nitrile group, this is C minus, and this is N also has a lone pair. Okay, so what happens is, this type of nucleophiles can attack on electrophile from both sides. And from both sides I mean either from the carbon side or from the nitrogen carbon side. Okay, so this is what is called a ambient nucleophile. Okay, so one more note here is, Actually, we just compared the rate of acidic strength of acetic acid with the likes of HCN, phenol, and um, RNH3 plus. So I just want to say that the inorganic acid, which is HBr, I just wanted to show that HBr is actually more acidic than these cases. Okay, just for the remembering sake, means there have been asked questions in the past wherein some of the substrates were reacted with HBr as the reagent and CH3O2H CH3CO2H as a reagent, and we needed to compare the acidic strength or the formed conjugate base strength in the formed products in those cases. So just a point to be noted here. Okay, so just remember this acidic strength. Okay, next, I hope in the previous set of lectures, in my previous lectures, I mentioned that SNI, or you can find it in previous set of organic lectures. So SNI, which is called retention. So SNI is neighboring group, one of the cases of nucleophilic substitution reaction which we saw. So the products for this case would be having retention in configuration. Okay, and it happens in the presence of SOCl2, while we had we saw SN2 reactions, and in which we actually saw the participation of good nucleophiles. Okay, like SOCl2 in presence of pyridine. So in presence of pyridine is very much necessary. If you just write in presence of SOCl2, then retention in configuration of the formed product will take place. But if I say SOCl2, then the inverted product take place, in which the nucleophile actually attacks from backside, okay, or from the opposite side of the leaving group. I hope you remember all these concepts, so I'm just revising it here. So PBr3, PCl5 in presence, PBr3 in presence of pyridine again, and we have something like PCl3 also. Okay, and Pi3. Okay, and P plus I2 also. Yeah. Okay, so the next lecture we'll be seeing ring expansion. So till then, good luck and goodbye.